Alright, we're going to kick off Unit 7, which is all about thermodynamics, by first talking about the concept of spontaneity. Spontaneity. So just as a quick refresher, we've discussed two things this semester. We've talked about how fast reactions can go. This was in Unit 5 on kinetics, okay? Rate laws, measuring rates and whatnot. We've also talked about how far reactions can go, and that's what we just covered about equilibrium, based on Q and K and predicting shifts. Where thermodynamics comes in, thermodynamics is talking about how does energy affect these things. So we know all chemical reactions involve changes in energy. We need to figure out how does energy affect, or does it affect how fast reactions go, and does it affect how far reactions go. So as a quick little refresher, we're going to cover the concept of enthalpy. And just to remind you, enthalpy was a variable that we learned at delta H, which measured the change in energy of a reaction. And we learned how to calculate it in two ways. Well, energy, the units for enthalpy were kilojoules per mole. So the way that we learned we could calculate that was Q over moles, where Q came from the equation Q equals mc delta T, using for a calorimetry experiment, for example. We also learned that we could get delta H from the sum of the enthalpy of the products minus the enthalpy of the reactants. Both of those are going to come into play. This is what we're going to focus on right now, because we're going to talk about the change in energy of the reaction. So let's say we have a hypothetical reaction here, which is A plus B going to C plus D. Okay. So we can see in the diagram that we start with about 40 kilojoules of energy. We see that some energy needs to be added. This height is called the activation energy, E sub A. And then once we get over that hill, we form the transition state. We form a new molecule, which is not what the reactants are, A and B. It's not what the products are yet. It's some in between. And then energy drops in this case to form the new products C and D. And in this case, since the final energy is less than the original, 20 and 40, if we were calculating delta H of products minus reactants, 20 minus 40 gives us negative 20, which in this case we know means the reaction is exothermic. That should sound very familiar. Okay? What we need to now connect that to is the idea of what's actually happening to the energy in the bonds. So let's pretend instead of A and B and C and D, we're talking about this diagram here of this reaction. So it looks like we're starting with CH4 and O2. So I'm going to rewrite this as CH4 plus 2 moles of O2 are turning into, let's see, making new bonds. We have a CO2 over here, and looks like we have two H2Os. There's a little cut off by my face. Okay? Two H2Os. So what we need to know now is this detail. How do bonds actually get formed? Well, here we can see that we have a carbon bonded to 4 hydrogens and these 2 oxygens double bonded together. The first thing that happens, okay, in reactants is that bonds are broken. All of these atoms have to be separated from each other, which we can see happens here. And that takes energy. To break something, you have to add energy to it. It's not going to just break on its own. So the amount of energy that goes into breaking the bonds is the activation energy. That's why some energy always has to be added to a reaction. Okay? Now once these atoms are, floating around separately, they're going to bond in new ways, potentially. And when bonds are formed, okay, energy is released. Energy is released. So the two things we need to emphasize here are when bonds are broken, that means energy is added. And when bonds are formed, that means energy is released. That's why this hill is going down. In order to determine if a reaction is endo or exothermic, we need to compare the energy needed that's added to break the bonds and the energy that's released giving out when we make new bonds. And if the energy released is more than the energy required, that makes the reaction exothermic. So as we can see in this diagram here, since the products are kind of lower down than the reactants, it shows that this enthalpy is negative. So again, big concept, big thing to walk away with. In any reaction, energy has to be added, the activation energy, to break bonds. And then, once those atoms are separated, those new bonds get formed, which releases energy. Okay? So main thing about enthalpy that we need to cover there. What that's going to lead us into is allow us to predict whether reactions are spontaneous or non-spontaneous. So this is two new vocabulary words for us. Spontaneous. If a reaction is spontaneous, that means it occurs without outside assistance. Okay? Without outside assistance. The activation energy only. Okay? Remember, all reactions need some energy to start. Okay? So for example, let's say you had an egg here. Okay, just pretend this is an egg. And you're holding an egg and you drop it. Okay? And you drop it to the ground. What's going to happen to that egg? It's going to splatter all over the place. Okay? Once you drop that egg, it will splatter without you having to do anything else. That is a spontaneous process. Okay? On the other hand, a non-spontaneous process, okay, occurs with outside assistance. Just think about that prefix non, meaning not. Or another way we could say that is a change in conditions. If you change something about the system, that might make the reaction occur. Okay. So thinking about the egg again, if you have splattered egg on the ground here, that egg is not going to magically go back up into the air and turn into a solid egg again. That won't happen unless you have some outside assistance, some special power, some egg reversal device that allows it to get back together. So we're going to start to describe reactions as spontaneous versus non-spontaneous. Another example would be, let's say you have some ice at solid water at 50 degrees. Okay? Solid water at 50 degrees is going to turn into liquid, just sitting on the table. You're not going to have to do anything to it. Okay? That's spontaneous. On the other hand, liquid water is not going to just turn into ice at 50 degrees Celsius. Okay? The freezing point of water is 0, so we would have to change the conditions, cool it down, in order to make this reaction happen. So again, the main idea is some reactions are spontaneous. They occur without outside assistance. Some are non-spontaneous. Another term we need to know for spontaneous, okay, is non-reversible, meaning you can't reverse it. This egg drop, that reaction is spontaneous, which means it's non-reversible. We can't have the egg magically, yolk and everything, shell, turn back into an egg. That won't happen. Okay? So focus on those two vocab terms. And if we think about an example here, okay, we have a ball, and we want the ball to either go down or go up the hill. Which of these is a spontaneous process and why? Well, clearly this one is going to be spontaneous because it's going to roll down the hill based on what we know about gravity without any outside assistance. For that ball to roll up the hill, I'm going to have to get up here and push behind it. I'm going to have to provide some outside assistance. So this would be considered a spontaneous process because no outside assistance was needed. Right? So this unit on thermodynamics, why is this important? Why is this important? Because what it allows us to do, okay, it allows us to predict, okay, we can predict the direction a reaction will go. So in the past we've talked about how fast in Unit 5, and we've talked about how far in Unit 6, equilibrium. But now we want to know, is it going to go towards the products, towards the reactants, which excuse me, direction will the reaction go? And that's what thermodynamics will allow us to do. The first thing about thermodynamics that will allow us to predict that has to do with the concept of spontaneity. Okay? So again, as we said, let's say we have a reaction A turning into B, and let's say that that process is spontaneous. That also means that it's non-reversible, which means that the reverse reaction from B to A would be non-spontaneous. The reverse reaction will only happen if outside assistance is provided. Another word that we need to be familiar with here for spontaneous is thermodynamically favored. So the language that we'll see is, which of the following would explain why this reaction is thermodynamically favored? Or is this reaction thermodynamically favored? That's going to be based on, is it spontaneous or not? Is it spontaneous or not? Okay? And what's cool about thermodynamics is it allows us to figure out the direction, but not necessarily the speed. That's one of its limitations, because, for example, solid carbon will turn into diamond, okay, at a very, very high temperature and pressure. This is a spontaneous process. This will happen without outside assistance. However, it takes millions of years. So just because something is spontaneous doesn't mean it's fast. Just because something is non-spontaneous doesn't mean it's slow. Spontaneous tells us nothing about speed. It just tells us, will the reaction happen in that direction or not? Okay? So for example, if we consider water, okay, solid water will turn into liquid water, and the enthalpy of that reaction is 6 kilojoules per mole. Now usually, most reactions are thermodynamically favored, or spontaneous, when delta H is less than 0, exothermic. Not all of them, though. So for example, this one is a spontaneous reaction. It's a spontaneous process, despite the enthalpy being positive, greater than 0. Why is that? Well, what explains why this process is spontaneous is a new property, a new variable, a new thing that we can measure about reactions that is called the entropy. Entropy. Entropy we will abbreviate with an S. So what we can start to do is we can start to measure the entropy of different processes and use that with enthalpy to figure out if a reaction will occur or not. What you need to know about entropy is the letter is S, and the units for entropy, okay, are joules per Kelvin. Joules per Kelvin. Right? Something very, very important to focus on. Joules per Kelvin, because everything we've dealt with before, for example, enthalpy, was kilojoules per mole. Kilojoules. Entropy is always going to be measured in joules, and we got to make sure later, you'll see we have to make sure the units are the same before we do any problems. So this will either need to be converted into joules or this into kilojoules. So just be aware, these are the units for entropy. Okay? So how does that get tied into thermodynamics? Well, the first law of thermodynamics tells us that energy is conserved. Okay? Conserved, if we can spell something right. There we go. Conserved. Okay? So in any chemical reaction, in any process, anything in the universe, energy is always conserved, even though energy can change forms. So for example, a solar panel, we take energy from the sun, thermal energy, okay? We convert that with a solar panel into electrical energy, okay? We can do this for mechanical energy or kinetic energy or potential energy. Energy always changes forms. And what entropy measures how it is changing. Entropy measures the change in forms of energy. Okay. And again, this might just seem kind of pretty conceptual and big, and like, what are we really even saying here? When we talk about what entropy actually is here in a second, and give examples, it'll be a lot clearer. So what do we need to know about entropy? Basically what it measures. Okay, what does it measure? Like if you say the entropy of this process is 50 joules per Kelvin. What does that actually mean? What it measures, it's measuring disorder. It's measuring chaos. It's measuring disorganization. Okay? So for example, if you had, two little spheres in a box, and then you move those spheres into a bigger box. What do we mean by disorder and chaos and disorganization? Well, in this bigger box, there's more room for these little molecules or whatever to move around. Here there's a lot less. Okay? So here there's more opportunity for disorganization and spread outedness and chaos. So we would say that this has a higher entropy. Okay? So higher entropy, systems or processes with higher energy, they have more ways to change. And system or processes with less entropy have fewer ways to change. Or another way of saying that is that they are more organized. And we'll connect this to molecules here in just a second. Okay? So entropy, this value of S, is measuring kind of disorder, chaos, okay, disorganization. And in all processes, entropy is going to be greater than 0 if it is spontaneous. Okay? Let me rephrase that. The entropy of the universe is greater than 0. Processes like to be, if greater than 0, if delta S is greater than 0, the change in entropy is greater than 0, it's positive. That means we're getting more disorganized, more chaotic. Okay? And if delta S is less than 0, that means we're less organized. Okay? So for example, let's say Mr. Brick Builder here has a pile of bricks and he's tossing the bricks out. Okay? There's two ways for those bricks to fall. They could fall beautifully into a nice little, wall like this, perfectly aligned, or they could end up just in a random pile. Well, which one's going to be more likely? It's way more likely that they're just going to end up in a random pile. So this is what we mean by saying the entropy of the universe, of processes, is going to be greater than 0, because this is more disorganized. That's more likely to happen. This organization, exact specific orientations, are very unlikely to happen in processes in the universe. Okay? In terms of a chemical example, let's say you mix a solute, these green dots, with a solvent, these yellow dots. We know that over time those molecules are going to start moving around, random motion, all over the place, and eventually they're going to be all spread out here. They're going to be very disordered. Okay? Here, very specific order of this on top and this on bottom. Not the case here. So in this case, this process is going to be spontaneous, which means delta S is greater than 0. Again, this is all trying to help us predict, like, will this reaction happen, or will the reverse reaction happen? Which one will occur? Which one is thermodynamically favored? So what are some ways that we can increase entropy, that we can have delta S be greater than 0? Okay. Well, one is we can increase the volume. Like that example I gave you earlier, a small box with 2 dots in it versus a big box with 2 dots in it. Way more possibilities of where these molecules can be here than here. What else could we do? We can also change phase. This is a big one. So if we go from a solid, molecules all really close to each other, to a liquid, molecules a little bit more spread out, here there's a lot more combinations of disorder, unorganization. So going from solid to liquid or liquid to gas, that's going to increase our entropy. Okay. We could also change the concentration. Okay. Change the concentration, the molarity. If you have something with 2 dots in it versus something with 10 moles in it, there are way more possibilities, way more combinations of how these molecules can be organized. So entropy is greater in this when the concentration is increased. And in a similar way, the number of moles or atoms, if we increase those, the entropy will increase as well. So for example, if we had a reaction of 1 mole of A turning into 3 moles of B, going from 1 to 3, it's the same idea. We go from one thing to 3 things. So we have way more possibilities, way more combinations, way more entropy, way more disorder, way more disorganization. Okay? So we've covered the idea of spontaneity, what is a spontaneous process, bonds breaking, bonds forming, what entropy is, how to measure it qualitatively. What we'll move into next is how to actually measure it quantitatively using numbers.